Welcome back to Mr. Warren's Audio Hood. Perhaps you were expecting Pee Wee Herman. No, we prefer to handle our equipment with both hands, and I don't own a trench coat. This is the second episode in our series. In this episode, we will explore impedance, frequencies, and tonality. If you will recall from the first episode, Ohm's law pretty much drives everything. Many of you who perhaps already understand Ohm's law are asking, why this? As we discuss impedance, you will understand the why. Almost everyone who has hooked up a basic home stereo system or a basic PA system has likely seen speakers and amplifiers or other equipment labeled like this. 8 ohms, 16 ohms, or similar. Most speakers are going to be 8 ohms. A smaller percentage of professional speakers are 16 ohms, and some specialized professional speakers like subwoofers might be 4 ohms. Those ceiling speakers we described yesterday in the last episode can often be around 1,000 ohms. Unless you routinely get run over by the obvious train, you will know that headphones, including earbuds, are also speakers. At its most basic level, a speaker is basically a diaphragm attached to a coil of wire mounted inside of a magnet. In a vast percentage of common speakers, that diaphragm is made out of paper. In higher quality speakers, it can be made from Kevlar, aluminum, titanium, polycarbonates, and certain exotic composite materials. A speaker works by induction. A voltage is applied to the coil of wire, suspended in the magnetic field, which causes it to move either towards the magnet or away from the magnet depending on the polarity of the voltage coming in. This speaker in the video is being fed a 20 Hz sine wave signal, which can be seen on the oscilloscope in the background. And here that is again with some serial bits added for visualization. Here's that again in slow motion. That coil of wire is what is referred to as an inductor, literally something which induces current to flow or allows induction in a circuit. As far as an AC signal is concerned, that inductor also creates impedance within the circuit, which is measured in ohms. But you're saying, what resistance is measured in ohms? How is that? Mathematically speaking, impedance is used in Ohm's law calculations exactly the same way that resistance is. The trick is this. Impedance is an AC or alternating current measurement, whereas resistance is primarily a DC or direct current measurement. You cannot accurately measure the impedance of a speaker with a volt-ohm meter. The measurement of a speaker with a DC meter can tell you roughly what the impedance is, or at least will tell you whether or not that voice coil in the speaker is blown or open, in which case you know that that speaker has been seriously abused to cause that to happen. Impedance itself is a complex measurement, as it requires ultimately measuring inductance, frequency, resistance, capacitance, and reluctance, and until recently required complex equipment to measure and required a calculator and complex math to arrive at the measurement. But without going off on the mathematical deep end of the pool, we'll streamline it a bit. Impedance is primarily frequency dependent. In other words, the impedance of a device will change according to the frequency. In other words, if you look at those printed specifications on the back of a speaker or an amplifier, on average, it's taken either across several frequencies and averaged together, or it's taken at 1 kilohertz, and that's the printed specification. If you look at a trend plot for a typical speaker across its entire range, that most component speakers will range from 5 ohms at 20 hertz to 8 ohms at 1 kilohertz and 9 or 10 ohms at 20 kilohertz. This is very simplified, but you get the idea. In the basics of loudspeaker design, this is how components are selected. If you look at your typical consumer speaker, you will have a woofer, which is the low frequency driver, and the tweeter, which is the upper frequency speaker. Tweeters are typically physically smaller than the typical woofer located in the same box. The woofer might have an impedance of 5 ohms at 20 Hz, 8 ohms at 1 kHz, but above 3 kHz it might have an impedance of 20 ohms. The tweeter at 20 Hz, if it can even respond to 20 Hz, might have an impedance of 25 ohms. At 1 kHz, it might have an impedance of around 16 ohms. And around 3 kHz, it might be around 18 ohms. And at 16 kHz, it might be 16 ohms. These figures are for illustration purposes, but those values demonstrate why certain components are selected based on those measurements. In that case, a woofer might be marked as 8 ohms and the tweeter marked as 16 ohms, which is not unusual in that particular situation. Any speaker that has a separate low and high frequency component will have some type of crossover or filter network inside of it. The woofer's part of the crossover network is called a low-pass filter. The tweeter's part is called a high-pass filter. The low-pass filter only passes frequency content below a certain point. The high-pass filter only passes high-frequency content above a certain point. This frequency, or this point at which these cut off, is referred to as a cutoff point or a roll-off. When describing high and low-pass filters, combined point of cutoff is referred to as a crossover point. If the speaker happens to have 3 driver components in it, a low, mid, and tweeter, or low, mid, and high component, the mid-range component will require what's called a bandpass filter. Typically, the bandpass filter is specified with a center frequency specification. It also has a lower and higher cutoff point on each end of it. These are also referred to as shelving frequencies. These terms will come into play later on as we delve into equalization. Now that we're back from the scenic detour, we'll continue with impedance. Impedance is something you will most likely have to deal with when connecting speakers to amplifiers. It does affect things you might plug into a mixer, but we'll get into that a lot later. If we have an amplifier and some speakers, the back of most professional amplifiers will have their nominal output impedance clearly marked near the output connectors on the rear of the unit. Most will say X watts at 8 ohms and maybe 2 times X watts at 4 ohms. So what does this really mean to our old friend Ohm's law? Ohm's law will explain. If, for illustration, we assume that the amplifier's typical output voltage is like 60 volts, that means with an 8 ohm load, it draws or puts out 7.5 amps, which then means the amplifier can put out 450 watts. The 60 volt specification is only for illustration, but is actually fairly common in terms of amplifier designs. The actual supply rails in an amplifier can be anywhere from 25 volts to 100 volts or more. These are really dependent on who made the amplifier and what it was designed for. So if we take this further, we have a 4 ohm speaker attached to that amplifier, then the math tells us 60 divided by 4 is 15 amps. 15 times 60 is 900 watts. A speaker that actually has a 4 ohm load is not a common thing, except for some, but not all, subwoofers. Primarily because some subwoofers have 2 speakers mounted in the box, which wired in parallel give you 4 ohms. So if we have one 2-channel amplifier and 4 total 8 ohm speakers, what does this mean? As with adding resistors connected in parallel, we do the same thing with the speakers and use this basic formula. You will notice the symbol Z. It is a standard notation for impedance, where R is for resistance, Z is for impedance. This is important more so for designing complex electronic circuits where impedance and resistance aspects have different purposes. Thus, Z1 equals 8, Z2 equals 8, so 64 divided by 16 is 4. The resultant impedance would be 4 ohms for 2 speakers in parallel, which means we could simply connect 2 speakers to each side of that amplifier, and we would have 900 watts of power available. So this means that if you have the amplifier's volume control all the way up and feed a full level signal to that input, you would get 900 watts at its output. But Your speakers better be capable of handling 450 watts apiece. Most speakers will have that information on the back panel as illustrated. If they do not, you can always go online and look up the specifications for that particular make and model of speaker. But what if we have 6 speakers? Here's where things get really weird. Here's an illustration. To add 3 impedances in parallel, we use this equation. 1 over Z total, which is basically that equation, equals 1 over impedance 1, 1 over impedance 2, and 1 over impedance 3. So 1 divided by 8, plus 1 divided by 8, plus 1 divided by 8 is 0.375. Thus, 1 divided by 0.375 equals 2.66 ohms. Generally, without breaking out the calculator, we just use the figure of 2 ohms when discussing 3 speakers in parallel. The problem is this. The amplifier we see in our example does not have a specification printed on the back that says it can handle 2 ohms. Most common amplifiers cannot. Most touring grade or professional grade amplifiers can do 2 ohms. The end result is if you take that 2 ohm load and hook it up to the amplifier, you can blow both the amplifier and the speakers up. The only way to accomplish that, given the equipment we have on hand, is to do something really goofy like this. That would mean either hooking up all 3 speakers in series, resulting in a 24 ohm load, as impedance adds when you put them in series, which would not hurt the amplifier, but it also would not be very efficient and would affect the frequency response of the amplifier as we said before, impedance is a factor of frequency. Remember, so they wouldn't quite sound right. It would work. You'd get by with it in a pinch. It's a Band-Aid. Or we could get really weird. We could hook up 2 in series and the third one in parallel to the other 2, as in this diagram. Thus, 16 ohms and 8 ohms, which would give us this equation. 16 times 8 divided by 16 plus 8 equals 128 divided by 24, which is 5.33 ohms, which is well within what the amplifier can handle. But you would have to be extremely desperate to try something that weird. Okay, all of you old dogs are out there. We know you did stuff like that back in the 70s. Go back to sleep. There's a lot of other strange things people did back then too, and you know who you are. Another thing that can get you into trouble is by underpowering speakers. In other words, speakers that are rated for 600 watts should have an amplifier rated to deliver 600 watts. Speakers like that are usually highly efficient when powered correctly. Theoretically, 2 speakers of that caliber are sufficient to cover about 1,000 people inside of a room. It would be a minimal system, but that expectation is correct. If you decide to cheap out and use your uncle's old 25-watt hi-fi amp to drive those speakers, well, that might be fine in your living room. If you try to cover that audience with a 25-watt amplifier, you actually have a greater chance of blowing the speakers than you would with the 600-watt amplifier. The reason for that has to do with the amplifier's internal power supply rails. As we discussed earlier, a typical professional amplifier might hover around 60 volts, whereas your little consumer amplifier might be closer to 25, 30, or 40 volts. As you feed more signal into an amplifier, as it gets louder and louder, eventually it puts out more and more of its maximum allowable voltage. When you push it too far and it tries to go beyond what its power supply can put out, it'll basically flatline or clip. And when it does that, a typical cheap amplifier like that will spit out DC at 40 volts. DC at 40 volts across the speaker's voice coil will pretty much smoke it very quickly. And then your nice PA speakers will become an expensive wreck. While we're on the subject of speakers and magnets, we should discuss dynamic microphones. A dynamic microphone, such as the one described here, are mechanically and structurally identical to the typical speaker. There is a diaphragm attached to a coil of wire. Coil of wire is suspended in a magnetic field. Other than physical size, they're nearly the same. The typical dynamic microphone has an impedance of between 50 and 300 ohms, depending on the manufacturer and depending on the microphone's intended purpose. This means that any speaker can be used as a microphone, and any dynamic microphone can act like a speaker, but not a very efficient one. There are intercom systems in some public schools that work on that exact principle. The speaker mounted on the wall above your teacher's desk can carry public address announcements. But by throwing a switch in the main office, they can communicate both directions with your teacher if they choose to. This is a picture of a Yamaha Subkick microphone. Basically, it's a woofer from one of their studio monitor speakers mounted inside of a tom-tom shell. It's intended to emphasize the low-frequency thump from a typical kick drum in a drum kit. The problem with using a speaker of that size as a microphone is that the weight and surface area do not respond well to higher frequencies. This, of course, works well for something that is intended to pick up only low-frequency energy. As I had mentioned earlier, a microphone can act as a speaker, and a speaker can act as a microphone. In this particular case, I've added this little cue box which outputs a tone, plugged it into the back end of this microphone. If you turn on the tone, you can hear it coming out of the microphone. And over here I have a pair of headphones plugged into the input of a mixer to reverse them as a microphone. Check, check, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I briefly touched on the relationship of frequencies in the earlier section. Understanding these relationships is key to progressing in your ability to use professional audio equipment. If you are able to play a musical instrument by ear, you will most easily be able to recognize the frequencies by their various tones. Other people will simply have to take the time to learn to recognize those frequencies as they hear them, either by making an effort to learn these or will absorb the information over time. Unless you just time traveled from 1904, you will most likely understand what a bass and treble control is on a simple stereo system or radio or other similar type of consumer equipment. In case you just parked your horse and buggy out back, we'll clarify. Bass refers to lower frequencies and treble refers to higher frequencies. If we examine the basic tone control section of a typical home stereo amplifier, we see there are two simple knobs, bass and treble. In some equipment, each knob will have a center point where it wants to click and sort of stop in the middle. That's referred to as a detent. It's not common for every piece of equipment, but it's not unusual either. The idea is that if it's in that center detent position, the piece of equipment in question will have a theoretically flat response. In other words, you've made no effect to the output of the signal. This, of course, depends on the quality of the circuits. The bass knob is essentially a low-pass filter. The treble control is essentially a high-pass filter. Either knob can boost or cut high or low frequencies depending on how it's turned. Turn the knob to the right, you boost. Turn the knob to the left, you cut. With almost all equalizer circuits, which a tone control is, there's always some overlap between the sections. What this means is invariably they share a somewhat symbiotic relationship, such that what you do with one always has some effect upon the other. As we look at a sweep of this typical tone control system by viewing the output on this real-time spectrum analyzer, we can see what the cutoff frequencies of the two controls actually are. In this case, we're using a mixer which has three, which has a bass, mid-range, and treble section. Most equalizers, regardless of type, work in a similar fashion. Since most digital equalizers are modeled on their analog predecessors, they have similar issues. Within fairly basic equipment, mixers in particular, a 3-band equalizer is typical to find on each channel of the mixer. This means that you'll find a bass, mid-range, and treble control, or bass, mid, and high control on each channel. In better units, the mid-range section is sweepable. In other words, its center frequency is adjustable. This is very handy because the mid-range frequencies are where you tend to get into the most trouble with the PA system or other environments. Most mixers of any quality will also have a separate high-pass filter on each channel. This is very handy for dealing with rumble, mic handling noise, wind noise, street rumble, air conditioning noise, and that sort of thing when using a live microphone. Most of them typically cut off around 75, 125, or 150 hertz. Some have a sweepable control on them as well, so they can be varied anywhere from 20 to 200 hertz, or sometimes 300 hertz. It just depends on who made the device and what quality you get. You do get what you pay for. Anytime you're using a microphone to reinforce spoken word or singing or anything like that, either in a recorded environment, a live PA environment, even the broadcast world, it's generally good practice to always engage the high-pass filter as a matter of practice. Very few human beings have any content in their voice below 180 or 150 hertz, unless you happen to be doing a broadcast with James Earl Jones. He might possibly be the exception. Another example of where this is somewhat useful is if you're in a room which happens to be located next to a busy highway or a subway platform, or maybe there's a generator parked outside in the parking lot powering who knows what, or the air conditioning plant for the hotel you're working in happens to be right next to the ballroom. There's some subsonic stuff which you may not be able to hear, but which will reflect on the VU meter of the console, or you might see the amplifier meter twitching, but there's nothing coming out because the speakers you're using don't really respond below 100 hertz in that example. So the best thing to do is whatever live mic that's coming from, make sure you have the high pass engaged and you're not wasting energy trying to reinforce or reproduce something that the speakers aren't capable of doing to begin with. Learning to recognize frequencies is useful. First of all, for being able to hear things that shouldn't be in the PA system, or things that are missing from the PA system, and knowing exactly what those are just by hearing them. It's also very handy in dealing with feedback and being able to recognize a problem frequency when that situation occurs. Feedback basically is an accidental sine wave. All sounds in nature inherently start with some type of a sine wave. What you wind up hearing is a combination of that sine wave and other surfaces that it encounters on its way into the world. Essentially, all sounds in nature are the result of a vibration of some type. In this video clip, we see a tuning fork demonstrated. This one is designed to resonate at 180 hertz. This particular one is a laboratory-grade tuning fork. If you start this one vibrating and place another of the same pitch nearby, the second tuning fork will start vibrating on its own. This is referred to as sympathetic vibration. Sympathetic vibrations are something to be aware of, particularly in large, difficult rooms. Here's that clip again in slow motion. This tuning fork is designed to vibrate at a particular frequency, which we hear as a pitch or a tone. The sound of your voice is ultimately the result of vibrations within your larynx coming into contact with your throat. Depending on the size and length of your throat determines what the pitch of your voice is. A viola and a guitar are roughly the same size. If you pluck a guitar string, it sounds this way. If you pluck the string on a viola, it sounds this way. The differences have to do with the resonance within the body of the instrument, as shown in this diagram. Another example of body resonance has to do with something as simple as a Coke bottle. If you take an empty Coca-Cola bottle and blow across the top of it, you'll get a musical note or a pitch. If you fill that bottle with a bit of water, that pitch will change as the volume inside the bottle has changed. More specifically, this means that the resonant frequency of the bottle has changed. This change can actually be calculated mathematically. These formulas to determine that resonant frequency were developed by a man named Helmholtz. The equations are complex, so we won't dive into them particularly here. Anything like that Coke bottle is essentially a resonant chamber. What determines the actual pitch produced by that resonant chamber or the resonant frequency has to do with its internal volume and the length of the port, which is the neck of the bottle and the opening of the bottle, and what that port volume is and port diameter. Any room is a resonant chamber, and its resonant frequency can be predicted by the internal volume of air inside. If you open a door, close a door, open a window, or things like that, it changes the resonant frequency of the room. If you fill the room full of human bodies, which tend to absorb sound at a great rate, that also changes the internal volume of the room and then changes the resonant frequency of the room. Regardless of those things, if we set up a microphone, a mixer, and a speaker system, and point the microphone at the speaker, it will feed back or ring. What frequency it would be most likely to feed back at depends on several factors. The resonant frequency of the room if you're indoors, the frequency response of the microphone, and the frequency response of the speakers, as well as the resonant frequency of the speaker cabinets, because the speaker box is a Helmholtz resonator. One thing I loathe is that every time in a movie someone goes to speak at a lectern, it always has some kind of feedback. It's not that that kind of thing never happens, it's just that no audio engineer will intentionally allow that to happen. Speaking of lecterns, this illustration shows you the distinction between a lectern and a podium. You speak from a lectern, you stand on a podium. Back to the microphone deliberately pointed at the speaker. This is not something you would typically do by intention. In this situation, it's just for an illustration. The point being that if a presenter or performer does take a microphone and wander out into the room and walks right in front of that same speaker, it could feed back. And knowing what frequency is taking off is the key to fixing this. If you have a performer whom you know will do that, the best practice is to set up the system so that it has the least tendency to feedback if someone does walk in front of the speakers with a microphone. It does happen. This is a demo of how feedback works. We have a microphone connected to this mixer, connected to this speaker, and I have this real-time analyzer set up in front of the speaker to display what's going on. If I take this microphone and run up its channel output gain sufficiently, it will start to feed back. As it starts to feed back, you can see it displaying on the RTA. In this case, it's displaying in the upper frequency range. So, since the equalizer on this console is so limited, I can take the upper frequency knob and back it off a bit, and the ringing will stop. I can then take the channel output, push it up a bit further, and you'll start to hear the low frequency go. So we go to that section of the equalizer and we back it off a little tiny bit. Open the channel a bit further, and naturally the mid-range is going to start going. So you back that off a little tiny bit. It's not a perfect situation. This is how you address the issue. One rarely discussed skill that often seems to be ignored is the concept of tonal layering, or tonal balance. An example that comes to mind for me is from an art festival I attended about a year ago, with an outdoor stage in the middle of a park. There was an act on stage consisting of a folk singer, a female folk singer with a very dark, husky voice, a bass player, a keyboard player, and she was playing an acoustic guitar. The bass player, the keyboard player, and her voice were all roughly in the same range, all playing similar notes. You combine that with an acoustic guitar playing chords roughly in the same tonal range, and what you wind up with is her vocals were nearly unintelligible. The issue is the person running the show was very inexperienced or had no concept of tonal layering. The solution is very simple. You have to high pass the acoustic guitar because acoustic guitars tend to get tubby and muddy in the 100 to 250 hertz range. Bass you can leave alone, but you have to high pass her vocals somewhat to get it out of the way of the bass, and then the keyboard patch you may have to also high pass and thin out somewhat. Those things taken together will then allow her vocals to be understood and intelligible. Part of your job is to make sure that the audience can understand what's being sung or said. If at a certain point the audience can no longer understand what's being sung or said, they are no longer an audience, they are a crowd. A crowd watches, an audience listens. It took a lot of self-control on my part not to reach across the console or stop and talk to the guy and explain to him how to fix the problem. I did not. To do so would have been extremely rude, despite the fact that the person was obviously in over their head. Again, audiences listen, crowds watch. Your job in that situation is to reinforce what's happening on stage. Part of reinforcing it is to make it intelligible. This same concept also applies to conferences and meetings and other such functions. It's one thing if you're doing a musical event and the bass player and the guitar player or the synthesizer player and the guitar player are combining sounds to make a completely different texture. That's an artistic thing. The situation I just described is a technical situation, not an artistic one. It's basically a quality issue. Within the corporate or presentation world or conference setup, you often will have situations where you have a presenter who insists on speaking over some kind of a YouTube video or other presentation that's part of their slideshow or whatever the event might be. And you may have to do the same thing by putting a high pass on the presenter's voice, or even putting a high pass on the video if it happens to be something with a lot of low end and muddy content. Otherwise, it'll be difficult to separate the two and get the message out, which is the whole point of that type of presentation. Thank you for visiting Mr. Warren's Audio Hood today. Please come back next time for our next exciting episode of Mr. Warren's Audio Hood.